Hello there, and welcome back to Cosmic Whispers. Perhaps you're just settling in for the evening, or maybe you found a quiet, reflective moment during a busy day. Wherever you happen to be, I invite you to pause, take a breath, and look up, if only in your mind's eye. Have you ever found yourself lost in those spectacular, swirling images from deep space, those cosmic canvases that seem to pulsate with color, and wondered, just what am I really looking at? We've all been captivated, I'm sure, by the breathtaking imagery captured and sent back to us by the Hubble Space Telescope. I'm thinking, of course, of those beautiful and multicolored nebulae. They often appear as if a contemporary abstract artist took a brush, dipped it in liquid starlight, and flicked explosive, impossible colors onto the black velvet of the cosmos. But this is not just a pretty picture, hung in the silent gallery of the night. What if I told you that this art is, in fact, an active battlefield? A stellar nursery? A celestial graveyard? What you are witnessing in these images are actual, physical structures, clouds of gas and dust so unthinkably vast they stretch for tens or hundreds or even thousands of light years. But this brings us to a crucial question. Are they truly this colorful? If we could somehow pilot a spacecraft to the very edge of one, would the universe really appear this way to our eyes? To answer that, we need to peel back the layers of the image itself, to understand the profound and perhaps surprising reality of what a nebula truly is. Our human intuition, fed by these dense, painted images, often deceives us. These nebulae might look solid, perhaps like the thick water vapor clouds we see in our own sky, but that perception is profoundly, fundamentally mistaken. The reality is a concept that our minds struggle to grasp. Nebulae are, in fact, extraordinarily diffused clouds of gas. We must completely adjust our sense of scale. On average, if you were to somehow scoop up a single cubic centimeter of a typical nebula, a volume about the size of a sugar cube, you might find only 10, perhaps 100, particles within it. To put that into perspective, the most advanced, perfect artificial vacuums we can create here on Earth, environments we consider to be truly empty, are still denser than that. For a true sense of this emptiness, consider the air you are breathing right now, wherever you are. A single cubic centimeter of air at sea level on our planet contains a staggering 10 quintillion particles. That is a 10 followed by 19 zeros. The void of a nebula is an emptiness we simply cannot manufacture or truly comprehend. Here is another way to try and visualize it. If you could somehow gather up an entire Earth-sized volume of a typical nebula, the total mass of all the captured gas might only be a few kilograms. It might weigh no more than a small child or a house cat. So, the great mystery becomes, if they are so incredibly sparse, so thin as to be bordering on non-existent, how can we see them at all? How do they form these brilliant, vibrant stains upon the fabric of the night? The first part of the answer is sheer, mind-bending scale. While they are impossibly thin, they are also impossibly vast. The Orion Nebula, for instance, is perhaps the most famous and brightest nebula visible from Earth. On a truly clear, dark night, far from the polluting glow of city lights, it is just bright enough to be perceived by the unaided eye, appearing as a faint, fuzzy patch in the hunter's sword. Yet some nebulae are far brighter. Consider the magnificent Tarantula Nebula, located in the Large Magellanic Cloud, a satellite galaxy of our own. If that particular nebula were as close to us as the Orion Nebula is, its brilliance would be astonishing. It would not only dominate the night sky, it would be clearly visible, a ghostly glow, even during the bright light of day. This visibility brings us to the engine that sits at the heart of these structures. The most famous types, which astronomers call H2 regions, are more poetically known as stellar nurseries. They are the cosmic cradles of our galaxy. Within these massive, sprawling clouds of cold gas, gravity begins its slow, patient, and relentless work. Over millions upon millions of years, tiny pockets of gas and dust begin to pull on each other, They collapse, coalesce, and compress. When the pressure and temperature at the core of one of these collapsing knots reaches a critical point, a new process ignites: nuclear fusion. In that moment, a star is born. A single nebula can contain enough raw, primordial material to create hundreds or even thousands of new stars. And crucially, it is these newborn stars, blazing hot and fiercely energetic, that light up the very gas from which they were born. Intense solar radiation, a torrent of high-energy particles and ultraviolet light streams away from these infant stars, blasting into the surrounding cloud. This energy isn't just reflecting off the gas, as light reflects off a wall. It is ionizing the nebula's particles. It's so powerful that it physically strips electrons from the atoms of gas. And when those electrons inevitably recombine with their atoms, they release that absorbed energy back out, but they do so at very specific wavelengths, or colors, of light. This is precisely why H2 regions are classified as emission nebulae. The ionized atoms within them are not just glowing. They are quite literally emitting their own light. The process is remarkably similar to something we see on Earth every day: a neon light. In a glowing open sign, electricity is passed through a tube filled with neon gas. This energy ionizes the neon, exciting the atoms and causing them to light up with that distinct reddish-orange glow. In the vastness of space, the ultraviolet radiation from a star acts as the electricity, and the nebula's gas, mostly hydrogen, acts as the neon, glowing brilliantly in response. This is where our initial question about color finally finds its answer. In those famous, breathtaking Hubble images, each brilliant color is assigned to a different ionized atom. But, and this is the key, there is no blanket rule. For example, in the iconic Mystic Mountain image from the Carina Nebula, the deep, blood-red colors correspond to sulfur atoms. The vibrant greens trace the presence of hydrogen, and the ethereal, ghostly blues reveal the location of oxygen. Yet, in another image, like that of the Swan Nebula, the color assignments might be completely different. Blue might represent visible blue light, while red is used to track infrared radiation and hydrogen. This isn't arbitrary, nor is it done purely for aesthetics. It is a direct result of the very specific and powerful way Hubble is designed to take photographs. Hubble is primarily a visible light telescope, but its extraordinary optics also allow it to see into the near ultraviolet and near infrared, parts of the spectrum wavelengths of light that are entirely invisible to our human eyes. When scientists want to study a nebula, they often want to know what it is made of. They are seeking a chemical map to understand the processes of star birth and death. To do this, they photograph the object not just once, but multiple times, using a series of highly specific filters. Let's walk through the process. Say they want to see the distribution of hydrogen. They will place a filter on Hubble's camera that only lets through light being emitted at the 658 nanometer wavelength. This is the specific signature emission band of hydrogen. The result, when it is beamed back to Earth, is a black and white image. It's not colorful at all, but it is a map showing the scientists exactly where the hydrogen is. Then they will swap the filters. They will image the entire nebula again, this time looking for sulfur along the 672 nanometer wavelength. This produces another, different black and white image. And then perhaps they will do it a third time, looking for oxygen at 501 nanometers. A third black and white image. Only after these separate observations are complete do the astronomers and image processors on Earth step in. They take these three separate monochrome images and they assign a color to each one. They might decide, let's make sulfur red, hydrogen green, and oxygen blue. They then digitally combine these three images into one. A result is the breathtaking, full-color composite that we see. As you browse the Hubble image gallery on their website, you can often see for yourself what the colors have been assigned to by looking at which wavelengths of light were used. For images of nebulae, this technique, known as false color or assigned color, is almost always used. It is not a deception. It is a profound translation. It allows us, the non-specialists, to see the invisible chemistry of the cosmos. That said, Hubble does take what we call natural color images as well. The magnificent Sombrero Galaxy, for instance, was captured by taking 3 different images using standard blue, red, and green RGB filters. When those are combined, the colors you see are a much closer approximation of what you would see if your eyes were suddenly millions of times more sensitive. So, if Hubble's iconic nebula images are mostly false color, what would they really look like to us? Generally speaking, a lot more red. The single most dominant element in the entire universe is hydrogen, and its primary emission line, the one it glows with most strongly, called hydrogen alpha, is in the deep red part of the visible spectrum. The European Southern Observatory, ESO, also studies many of the same objects. Looking at the Carina Nebula on ESO's website, we see their images often use RGB color bands, capturing natural light. What we see there is a much closer match to what our eyes might perceive, a vast, swirling, beautiful cloud of rosy red. Sometimes, astronomers will even overlay the scientific data, like ultraviolet and hydrogen alpha, on top of these natural colors, blending scientific insight with a more realistic view. So far, we have only really discussed the most famous type, the H2 emission nebula. But it is worth mentioning that nebula is a very broad term. You also have reflection nebulae. In these clouds, the energy from nearby stars isn't potent enough to ionize the gas. The stars aren't hot enough. Instead, the starlight simply reflects or scatters off the dust grains in the cloud, much like a car's headlights illuminate a patch of fog. These nebulae, because blue light scatters more easily, the same reason our sky is blue, tend to have a similar frequency spectrum to the stars illuminating them, often appearing with a delicate, ghostly bluish tint. And then there are dark nebulae. These are vast clouds so dense with dust, or so far removed from any illuminating stars, that they are not lit up at all. They appear to us as ominous, pitch-black voids, like holes punched in the sky, visible only as silhouettes against the starry backdrop of the Milky Way or brighter nebulae behind them. They are windows into an even deeper, more profound darkness. All in all, the physical reality of nebulae may not be quite as psychedelic or multicolored as the processed images might suggest. But to me, that doesn't make them any less interesting. In fact, I believe it makes them more so. Looking through these specific filters means we can understand the complex physics and chemistry of star formation in a way our eyes alone never could. And let's be honest, they do make for absolutely beautiful, thought-provoking images. This is why I am so excited about this journey we are on together. Hubble has released a collection of what they consider their top 100 images, captured over its decades of faithful service above our atmosphere. And what I would like to do here on Cosmic Whispers is go through these pictures one by one. I want to sit with them and explore and explain just what it is we are truly looking at. And believe me, as we will see, some of these pictures demand an explanation. Which brings us to tonight's focus. We are making good progress through this remarkable gallery of cosmic wonders. Tonight, we arrive at image number 21, the Carina Nebula. And for this one, I am going to have to do something a little bit unusual for this series. Just look at this image. It is a gorgeous, sprawling, chaotic masterpiece. It looks to me as if that abstract artist has returned, flick painting a canvas in the most spectacular, violent, and beautiful way. But incredibly, every swirl of color, every towering pillar of dust, every pinprick of light represents something real. I must ask for your patience, because this will be the only image we look at today. There is simply too much to unpack, too many astonishing stories hidden within this single frame. I don't want to have to cut out any of the interesting details. It's a deep dive, which I hope is good for me and good for you. If this kind of deep exploration sparks your curiosity, I'd be honored if you tapped the like button, or perhaps even subscribed to join us on this journey. So, let's begin. Where is this celestial masterpiece? The Carina Nebula is, in fact, brighter and significantly larger at a staggering 200 light-years across than the more famous Orion Nebula we've discussed before. And yet, it isn't as well known, at least not to many of us. This is because it is a jewel of the southern sky. It is only visible from the southern hemisphere, meaning those of us up north will never see it grace our horizon. It is found near the constellation Carina, located deep within the dense, star-filled disk of our own Milky Way galaxy. At only 6,500 light-years from Earth, it is relatively close in astronomical terms. It is so large and bright that it can be seen with surprising clarity through a small telescope, or captured in beautiful detail with a long-exposure camera. What we are seeing in this image, much like the other nebulae we've encountered, is the dramatic, violent effect of extremely hot, young, massive stars. They are monsters, blazing with energy, and they are blasting away at the surrounding dust and gas. This is a process of creation and destruction, happening simultaneously. This very violence, as we know, compresses gas in other areas and encourages new star formation. And this nebula is absolutely brimming with active star-forming regions. Just off the main part of this image, there is a feature astronomers have nicknamed the Finger of God, a dense-looking pillar of dust. This star is, to put it mildly, a monster. It is currently believed to be the most luminous star yet identified in the entire Milky Way. It blazes with the light of a staggering 6.3 million suns. It is part of a binary star system, though its companion is so close it cannot be distinguished in this image. That companion is thought to contribute about 15% of the system's total, mind-boggling luminosity. WR25 is absolutely blasting the nebula. The Finger and the surrounding globules of gas are being actively evaporated into space by its fierce radiation, a process that might itself be triggering a new generation of stars to form within those compressed, dense knots. And here is a fascinating fact. Despite being possibly the brightest star in our galaxy, you cannot see it with the naked eye. There is simply too much intervening dust and gas between us and it, absorbing and deflecting its light. The only reason we can see it so clearly in this image is because the photograph included infrared data. Infrared light has a longer wavelength, allowing it to pierce through the obscuring dust far better than visible light can. As we learned, the colors here are significant and part of a false color composite. The red represents sulfur, the green is hydrogen, and the blue tracks oxygen. This entire chaotic region of stars, including WR25, is part of a massive star cluster known as Trumpler-16. Also contained within this same cluster, Trumpler-16 is an even more famous, and perhaps more terrifying, star, Eta Carina. While not quite as bright as WR25, it's still an absolute titan. It shines over 4 million times more luminously than our Sun, and weighs in at over 100 times its mass. It, too, is part of a binary system, bringing the system's total combined luminosity to over 5 million times that of our Sun. Now, I want you to try and imagine that. Pause for just a second. Picture our Sun in the sky, and then imagine it 5 million times brighter. If you are doing it correctly, as the original script for this video rightly notes, you should be imagining yourself and the entire Earth instantly and spontaneously combusting. Let's try to quantify this. Imagine a hypothetical planet orbiting this binary star system, a planet a little further away than Neptune is from our Sun. On our own Neptune, the surface temperature is a frigid -200 degrees Celsius. On this hypothetical planet, orbiting Eta Carinae at that same distance, the surface temperature would be 500 degrees Celsius. In that sky, our own sun would look like a tiny, insignificant pinprick of light, and our Neptune is a dim, frozen, forgotten world. Eta Carinae is truly impressive, and it is deeply, terrifyingly unstable. Eta Carinae is what astronomers call a luminous blue variable. This means its brightness is not stable. It changes wildly over time. Just 150 years ago, in the 1840s, it suddenly and mysteriously brightened, becoming the second brightest star in our sky, visible worldwide. Then, just as mysteriously, it faded back, eventually disappearing below naked eye visibility. The reason for this? The star almost went supernova. It underwent what is now called the Great Eruption. This image of the star is the most detailed, highest resolution image of an extended object ever captured by Hubble. We can see structures only 10 billion kilometers across with astonishing clarity. What we are looking at here, this strange dumbbell shape, is the ejected mass of the star from that eruption 150 years ago. It's now known as the homunculus nebula. During that event, it temporarily became as bright as a full supernova explosion, but somehow the star at its core survived. It did, however, release a truly titanic amount of its own mass, blasting it into space in the form of two polar lobes and a large equatorial disk. All of this material is still moving outward today, racing away from the star at 2 million kilometers per hour. Since that explosion, the star has stabilized somewhat, and its brightness has begun to increase again. It is now comfortably visible to the naked eye once more, a faint star in the southern sky. But it is a ticking time bomb. It will go supernova. It is at the very, very end of its life, and it could do so at any moment. It could be tonight. It could be 10,000 years from now. When it does, there are three main possibilities for its fate. First, it could go supernova in a typical manner. Its core would collapse, and it would temporarily appear as bright as Venus in our sky, a brilliant new star, visible even in broad daylight. Second, it could go hypernova. This would be a cataclysm on an entirely different scale, potentially becoming the brightest supernova in all of recorded human history. The resulting long-duration gamma-ray burst would be powerful enough to knock out all of our satellites in orbit, though we humans, with our feet firmly on Earth, would be protected by our atmosphere. The third and most unlikely possibility is that it collapses directly into a black hole. And this brings us to a fun or perhaps horrifying fact. If it did collapse into a black hole, and if, by some terrible cosmic coincidence, one of Eta Carinae's polar axes were aimed directly at Earth, the resulting gamma-ray burst would be apocalyptic. It would strike Earth's atmosphere with the equivalent energy of 1 kiloton of TNT per square kilometer over the entire hemisphere facing the star. This would, effectively, be the end of the world as we know it. Now, before you lose any sleep, please don't worry. Its axis is not currently facing us, and it's not really expected to produce a gamma-ray burst of that specific kind. But it is food for thought, nonetheless. Near this volatile star is the Keyhole Nebula, a fascinating and smaller structure of dark, cool gas and dust, starkly contrasted against the bright, fluorescent gas around it. Eta Carinae has a profound effect on this nebula, ionizing its gas and sculpting its shape, pushing against the surrounding dust. These bubbles, lines, and intricate details you see, they are the visible scars of this ongoing stellar war. Also within the Carinae Nebula is the famous pillar known as Mystic Mountain, which you have probably seen before. It is an image we will certainly discuss in detail later in this series. To me, though, it looks less like a mountain and more like a tall, thin man with a wizard's hat going on a leisurely stroll, but maybe that's just me. The last thing we allow look at in this image today is Trumpler 14. This is the other big star cluster visible in the frame. It is one of the youngest known clusters in the galaxy, containing about 2,000 stars. They are thought to be only 300,000 to 500,000 years old near infants by astronomical standards. Because they are so young, they are extremely hot and burning their fuel at a ferocious rate. They will be extremely short-lived. They will likely burn themselves out and dissipate in the next few 100 million years. So, enjoy them while you can. All of this, the violence, the beauty, the scale, it begs a question. Have you ever wondered what it would be like for our own solar system to reside inside a nebula like this one? Imagine looking up at a night sky filled with glorious swirling colors, with huge structures of light stretching from horizon to horizon. It must be an incredible, beautiful sight. Well, depending on how you define what a nebula is, it may surprise you to find out that we are actually inside of one right now. It's called the local interstellar cloud. How can this be? We certainly don't see swirling colors. To understand this, we must first clarify once and for all what a nebula actually is. The term itself, as we've touched on, is a relic from early astronomy. It was a blanket term for a variety of different things. Early astronomers, with their small telescopes, called anything that looked a bit milky, foggy, or cloud-like a nebula. This single category mistakenly included what we now know are distant galaxies, like Andromeda, and star clusters. These days, we have a much better handle on the classification. As we've discussed, the most famous type is the H2 emission nebula, like Orion. It consists of ionized particles, predominantly hydrogen, emitting their own light because they are excited by young stars, just like that neon lamp. On the other hand, there are dark nebulae, also called molecular clouds. Here, there are no nearby stars, so ionization isn't happening. They are cold, dark, invisible clouds of dust and molecular hydrogen. Sometimes you can have a mix of the two, a dark nebula nestled within a larger H2 region. In such a situation, you can often see the outer particles of the cloud becoming ionized by radiation, while the cold, dark particles remain hidden deep in the center. It is in these eroded regions that new stars are often born. And as we mentioned, if light from stars shines on a dark nebula, but the energy isn't high enough to ionize the particles, you get a reflection nebula. Finally, there are two types of nebulae related to the death of stars. First, planetary nebulae, which, despite their name, have nothing to do with planets. This is where a low to medium mass star, like our Sun, has begun to shed its atmosphere and outer layers at the end of its life, before it collapses into a white dwarf. Second, a supernova remnant, which is the expanding, chaotic shell of a high-mass star after it has exploded, often leaving a black hole or a neutron star at its center. These last two types are often so colorful and beautiful in images because they, too, consist of ionized particles, charged by the violent events that created them. They are, in essence, a special kind of emission nebula. Eventually, they will dim and disperse their heavy elements back into the galaxy, seeding the next generation of stars. As you can see, all these types can be broadly categorized into two groups: emission nebulae, which glow, and dark nebulae, which don't. But they all share one big, unifying similarity. They are all diffused nebulae. They extend for vast distances, sometimes thousands of light years, but the particles within them are, as we established, incredibly spread out. That Earth-sized nebula weighing only a few kilograms. To give you that perspective one more time, sea level on Earth has 15 quintillion particles per cubic centimeter. Even 450 kilometers up, slightly higher than the International Space Station, there are still 50 million particles per cubic centimeter. A nebula, with its 10 or 100, is an emptiness beyond our experience. When we see a nebula, we have the advantage of distance. We are visually squeezing a very diffuse, three-dimensional object into a narrow, two-dimensional field of view. This means that for an object like Orion, We probably have a much better, more cohesive view of its structure from Earth than any locals would have from the inside. For them, it would be far too spread out to perceive. Chances are, if you were on an Earth-like planet inside a typical nebula, you wouldn't even be able to tell you were in one with your naked eyes. The sky would look just as black. That's not to say all nebulae are equal. As mentioned, the Tarantula Nebula is said to be such a prodigiously bright H2 emission nebula that if it were where Orion is, it would cast shadows at night and be visible during the day. A nebula that bright you probably could see from the inside. So, what about our own local interstellar cloud? It, too, is classified as an emission-type nebula. The leading theory is that it is a very, very dispersed supernova remnant, which is mixed in with some cold, neutral atoms over time. The ionized particles within it are, on average, exceptionally hot around 730 degrees Celsius, with some individual particles even approaching millions of degrees. But here is a crucial scientific concept: the difference between temperature and heat. The temperature is high, which just means the few particles there are moving very, very fast. But the heat-specific capacity is incredibly low, because the density is so unimaginably sparse, at only about 0.3 particles per cubic centimeter. There are so few particles, so far apart, that if you were out in the middle of it in a spacesuit, they would barely transfer any heat to you at all. You would freeze to death, surrounded by gas that is technically hotter than the surface of the sun. Unsurprisingly, this extreme sparsity means our local interstellar cloud is not very bright. In fact, it is exceptionally difficult to see at all, even with our most powerful scientific instruments. It truly is on the very boundary of what you might even call a nebula. And yet, we are starting to find out that, like the spectacular images we admire, it too has a structure. This cloud is about 30 light years across. And perhaps most interestingly, we are just passing through. Our solar system is currently moving through this cloud, and we will likely leave it altogether in about 20,000 years. That's because the sun, and our entire solar system, seems to be taking us in one direction, while the interstellar cloud itself is heading in another. If you have ever seen diagrams of the solar system interacting with the interstellar wind, this is what they are talking about. It's not just particles blowing past us. It's a combination of that and us moving through them. The powerful magnetic field of our sun, called the heliosphere, acts like a shield. It pushes these ionized particles, the hot ones with a charge, around our entire solar system, leaving behind a magnet to tail as it travels, much like the wake following a boat. While we don't have a true visual image of this for our own sun again, it's hard to see from the inside. We have clearly seen this effect around other stars in the galaxy. But this is a key point. Only the ionized particles interact with our sun's magnetic field. The non-ionized, neutral particles, the cold ones, pass right through the magnetic field, streaming directly into and through our solar system. This is, in fact, how we've been able to tell which way the interstellar wind is coming from. We have had spacecraft in orbit, like NASA's IBEX mission, designed specifically to detect and catch the direction of these neutral particles as they pass by. Now, even though our interstellar cloud is incredibly sparse compared to a nebula like Orion, it is, paradoxically, one of the densest regions for hundreds of light years in any direction. This is because our entire solar system is contained within a much larger, even emptier region known as the local bubble. Inside this bubble, the average density is even lower than our cloud, at a vanishing 0.05 particles per cubic centimeter. This bubble appears to connect to other, similar bubbles, and it's in the regions where these bubbles meet that it's believed clouds like our local interstellar cloud are formed. Let me explain. When we talk of nebulae of any kind or density, we are really talking about the interstellar medium, or ISM. This is the simple term for all the gas and dust found in the galaxy, in whatever form it may be. It isn't evenly distributed. The thickest, densest sections of it are the different types of nebulae we've already talked about. But if you look anywhere in the sky, and you look at the right wavelengths, you will see a faint, omnipresent glow. These are ionized particles, emitting faint electromagnetic radiation. Our local interstellar cloud is just one tiny part of this vast interstellar medium. But as I mentioned, the ISM in our neighborhood is not evenly distributed. Within our local bubble, the density is far, far below the average for the whole Milky Way. Why? These bubbles are thought to be the ancient, expanding remnants of multiple supernova explosions that occurred millions of years ago, long before humanity existed. These explosions not only ionized the nearby particles, but they also pushed most of them outward, like a series of cosmic snowplows, leaving behind these vast, empty bubbles, also known as supershells. When the shock waves from different supernovae meet, the particles they are pushing suddenly have nowhere to go. Instead, they clump up at the boundaries. It is believed that our own local interstellar cloud is one of these clumps, a bit of cosmic dust swept into a corner, formed where our own local bubble and another adjacent bubble met. There are plenty of these bubbles out there, and the resulting local map of our galaxy's interstellar medium looks quite messy indeed. You may be wondering, though, why is any of this important? What is the point of scientists trying to map this invisible environment? Well, it is profoundly important for understanding our local space environment, which in turn helps us better define the universe around us. When we are observing something incredibly far away, a distant galaxy, or the faint, ancient echo of the Big Bang, we can now more accurately remove the contamination from any readings caused by the local interstellar cloud surrounding us. We know what kind of fog we are looking through. Also, a better understanding of the interstellar wind coming into our solar system means we can better design shielding and protect our astronauts, and eventually ourselves, against its radiation as we venture further from home. So there we have it. While we may not be adrift in a spectacular technicolor nebula like Orion, we are right now, sitting here on Earth, moving through the middle of our own local interstellar cloud. It is a structure that is real, that has a defined shape, and that emits its own faint, invisible light. It's a powerful reminder that we are not separate from the cosmos. Looking at it, we are in it. The instrument that has helped us understand so much of this, the Hubble Space Telescope, has been in faithful orbit around Earth for more than 30 years now. It gave its scientists and all of us a bit of a scare at the beginning of this past March when it encountered some serious problems with its onboard computer. A stark reminder that even these magnificent titans of science are mortal. But for now, it is back online, and it continues to be our most profound eye on the universe, allowing us to decode these cosmic whispers. Thankfully, the mission team was successful in that delicate recovery operation, and I am happy to report that everything is, once again, functioning as normal. It seems our faithful eye on the cosmos will be with us for many years yet. Scientists, in fact, expect Hubble to continue its mission, bringing us these windows into the universe, until at least the late 2030s. And what a legacy it has built so far. When you think of its incredible discoveries, what comes to mind? For so many of us, it is the nebulae. When we take that wide-angled, uninterrupted view of the night sky, something truly remarkable is revealed. There are, quite literally, hundreds of these ethereal clouds, these nebulae, spread out across our view. We've come to know them as the birthing places from which all stars come. And yet, as we are beginning to learn, the term nebula is a wonderfully broad one. It's a catch-all name for many different types of interstellar clouds, each with its own unique and achingly beautiful characteristics. I'm Alex McCone, and you are watching Astronomy. In this episode of our Hubble Images series, we are going to embark on a grand tour, exploring a variety of the most spectacular nebulae that Hubble has ever examined. And as we go, I will explain to you, in detail, just what it is you are looking at. The very first thing to explain, before we dive into these stunning images, is that all nebulae, every single one, are part of something much, much larger. It's a concept known as the interstellar medium, or the ISM. In the simplest terms, the interstellar medium is all the gas and dust that is unevenly dispersed throughout our galaxy, filling the empty space between the stars. If you could see in all wavelengths of light at once, you would see this magnificent, intricate network of cosmic dust and gas, a faint, glowing web that connects everything. From our vantage point here on Earth, this is what that medium looks like. Some parts of it are so astonishingly sparse, they contain only one particle per cubic centimeter. That is as close to a true perfect vacuum as you can possibly get. But then, there are the dense regions. These are the very nebulae I am about to show you. In these clouds, the particle count can climb to millions of particles per cubic centimeter. And while that may sound dense, we must remember our cosmic perspective. Our own atmosphere, here at sea level on Earth, has 10 quintillion particles in that same cubic centimeter. So even the densest parts of space are still a vacuum more profound than anything we can create in a lab. However, and this is the key, these nebulae stretch across many light years. Over that colossal volume, all those few particles really begin to add up, accumulating enough mass to build entire star systems. Let's look at our first example, and I will show you exactly what I mean. We begin with the most fundamental, the most basic type of nebula. This is an inert, cold, and dark cloud known to astronomers as a molecular cloud. They are named this way because they consist primarily of the H2 molecule 2 hydrogen atoms bound together. In this cold, dark state, they don't really do much. They are the sleeping giants of the cosmos. We can only really see them because their dense dust is silhouetted against the stars, blocking the light from behind like a vast, dark hole in the heavens. These molecular clouds are, nonetheless, some of the most densely packed nebulae out there, containing, as we said, millions of particles per cubic centimeter. They can just sit there in space, dormant, for millions upon millions of years. They are held in a delicate balance, prevented from collapsing in on themselves by their own faint internal pressure. That is until something comes along and gives the cloud a nudge, a gravitational disturbance. This bump could be the violent, concussive force from a nearby supernova shock wave, or it might be the more subtle, large-scale pressure of a density wave, a traffic jam moving through the galaxy's spiral arm. In any case, this external force overcomes the cloud's gentle internal pressure. Gravity is suddenly allowed to take over. The cloud, no longer in balance, begins to collapse in on itself. And the result is what you see tucked into the very center of the Circinus molecular cloud. A star is being born. This entire cloud, stretching far beyond this frame, contains 250,000 times the mass of our sun. That is a staggering reservoir of material. It means that if, or rather when, the whole thing collapses, there is going to be a truly spectacular cluster of stars in this spot in several million years. If we zoom in on the single star that has already formed, we can see some other fascinating phenomena. The bright, wispy nebula immediately surrounding the star is still part of that same Circinus cloud. It has simply been illuminated by the brilliant light of the young star. This specific region is now known as a reflection nebula. It's not glowing on its own, but simply, as the name implies, reflecting the light shining upon it. And if you look very closely, you can just about make out a protostellar jet, a high-energy stream of gas shooting away from the star's poles. This is the leftover material, the scraps from the feast of gas and dust that the star absorbed to grow, now being violently ejected at incredible speeds. It's a different color, glowing with its own light, because it is hot, having come from the star itself. This breathtaking image, which some call the cosmic reef, is a perfect example of one of the most famous types of nebula, known as an H2 region. In short, H2 regions are what happen to a molecular cloud once star formation really gets going. The biggest, most fundamental difference between a molecular cloud and an H2 region is that the H2 region produces its own light. Remember that star birth in the Circinus cloud? Now, imagine that happening thousands of times over. The particles within this cloud have been set aglow, or ionized, by the fierce solar winds and the flood of ultraviolet light pouring from the hot young stars shining within them. H2 regions also tend to be a little less dense in their parent molecular clouds, having been fluffed up by all that stellar energy, now containing only hundreds to thousands of particles per cubic centimeter. In this particular image, it looks as though you have two separate, distinct nebulae, side by side. But in reality, they are both active, glowing parts of the same vast, dark cloud. It's just that, so far, only these two regions have been carved out and ionized by the new stars within. The different colors tell a beautiful and violent chemical story. In the red section NDC 2014, the ionized gas is primarily hydrogen. In the blue section NGC 2020, the ionized gas is oxygen. This difference in color is due to the very different ways these two regions came to be. In the large red section, you are looking at a cluster of hundreds, perhaps thousands of stars, each one more than 10 times the mass of our sun. It is the combined ferocious UV radiation from this entire crowd of stars that is ionizing the hydrogen around them, causing it to glow red. The powerful stellar winds from these stars can be seen carving out the nebula, creating cavities. Where the nebula is dense, it is more resistant to this erosion. But here, where the nebula is less dense, the stellar wind has blown magnificent bubble shapes into it, wonderfully reminiscent of coral. The blue region, by contrast, is a story of a soloist. It has not been shaped by a crowd, but by a single massive star known as a Wolf-Rayet star. This type of star is among the hottest and most luminous that the universe can create. This particular one is 200,000 times more luminous than our sun. Because it is so intensely hot and bright, its expected lifespan is incredibly short, perhaps only a few million years. And over that short, violent life, it is shedding a colossal amount of its own mass in the form of unbelievably powerful stellar winds. It is this specific, focused, and violent wind that has interacted with the cloud, but it has specifically heated the oxygen, increasing its temperature to over 11,000 degrees Celsius. This is far, far hotter than the surrounding ionized hydrogen, and it's this superheated oxygen that glows with that distinct, ethereal blue. You can see a small section of the red nebula that also has some of this heated oxygen, right towards the center, which beautifully and poetically looks like clear blue water lapping up against a red, rocky beach. It is, all in all, just a stunning, stunning image from Hubble. Now, for a completely different type of nebula. The previous two we looked at the molecular cloud and the H2 region are closely related. They are both part of the grand story of star birth. This beautiful, intricate object, however, originates from something completely different, the death of a star. This is a planetary nebula, and the first major difference is scale. While those star-forming regions can span hundreds or even thousands of light years, a planetary nebula like this one is tiny, only a couple of light years across at most. And while molecular clouds contain enough mass to produce thousands of stars, a planetary nebula barely contains enough mass for one. This is because this nebula is that one star, or at least what's left of it. At the heart of this spectacle is an intermediate mass star, a star perhaps once like our own sun, but now on its very last legs. It is not exploding. Rather, it is coughing and sputtering, as the original script so well described it, exhaling its outer shell of gas into space. This glorious, complex, glowing shroud is the star's former atmosphere. Once this process is complete, the star at the center will have shed all its outer layers, and its core will contract into a tiny, hyperdense stellar remnant, a white dwarf. Because Hubble's mission has been going on for so long, for decades now, it means we have this extraordinary, unique ability to see a tiny part of a planetary nebula's evolution in human time. Look at this, number 64, the Stingray Nebula. This object has changed drastically in just 20 years, between 1996 and 2016. Just look at how it is dimmed, its structure fading. This is deeply unusual. Because of the vast timescales involved in astronomy, we are almost never privileged to see such a dramatic change. Usually, we can only see the most limited, subtle movement over such a short frame. For example, look at number 65, the Cat's Eye Nebula. This image is a composite of observations taken over a similar timescale, and it has barely shifted at all. This is what we expect to see. This is the normal, glacial pace of the cosmos. The Stingray's rapid fading is a rare glimpse of a cosmic event happening in fast forward. The cat's eye, of course, is named for an obvious reason, and it is just breathtakingly beautiful, both in this close-up and when you see it more zoomed out, where you can make out the vast, fainter halo of gas and dust that was ejected in an even earlier, separate event. Like the H2 regions, planetary nebulae are also a type of emission nebula. They produce their own light through that same mechanism, the ionization of gas particles. But here, the energy source isn't a cluster of new stars, but the searing hot, exposed core of the dying star at the center. Let's have a look at another one. This is number 66, NGC 7293, known to most of us as the Helix Nebula. And what a piece of art this is! The truly fascinating thing about planetary nebulae is that while some may share similar characteristics, no two are ever identical. Each dying star produces its own unique cosmic fireworks display. We are so incredibly lucky to witness these ones at all. As these nebulae expand, disperse, and cool, they will be lost from view, fading back into the interstellar medium in only a few tens of thousands of years. Astronomically speaking, that is the blink of an eye. It means that the ones we can see, like this one, must have happened very recently, and they must be relatively close. And the Helix Nebula is especially close to us. It is so large in our sky that it covers an area about half the size of the full moon. This proximity allows us to peer deep inside and see its remarkable, intricate details. What I find so incredible about this image is that we are seeing a story in progress. We are witnessing how the stellar wind, streaming from that central white dwarf right now, is blasting away at a fainter outer halo. That halo is dust that had been ejected from the star before the main planetary nebula formed, likely when it was in its red giant phase. Now, just like in the cat's eye, the new, faster expanding planetary nebula has caught up with that old slow-moving halo and is carving it away, creating those magnificent, cometary-looking knots. This is a mind-blowing image of stellar death, and it's probably one of my personal favorites. There are so many more beautiful, poignant examples I could show you, but let's finish this part of our tour on number 67, the Hourglass Nebula. This nebula is quite far away, at about 8,000 light-years, so we can't see it in the same exquisite detail as the Helix. However, its shape, its color, and that little beady eye staring back at us from the center are truly phenomenal. The distinct two-lobed shape is a powerful clue. Sometimes, if the planetary nebula originated not from a single star, but from a tightly orbiting binary star system, the material isn't thrown off in a simple sphere. Instead, the dance of the two stars, and perhaps a dense disk of material around their equator, funnels the ejected gas, blasting it out in two powerful opposing lobes. This could very well be the case for this one. And you can just see the star, or stars, glowing brightly within that central, compressed ring. And no, that's not a reflection from a camera flash, as your mind might trick you into believing. That is the engine of this beautiful, ethereal object. Now, we must leave the realm of these small, ghostly remnants and travel to an entirely different galaxy. This image is a small section of a nebula known as 30 Doradus, or, more famously, the Tarantula Nebula. This colossal object is not in the Milky Way. It is a huge, impressive nebula found in the Large Magellanic Cloud, a satellite galaxy orbiting our own. Some may argue it isn't as pretty or as delicately structured as some of the other nebulae we've looked at. It is a chaotic, sprawling, blindingly bright mess. But I must say, it has a terrifying beauty all its own. And if it isn't its looks that make this nebula stand out, what is it? What sets this object apart from everything else we've seen so far? Well, let's get some context. This is the Large Magellanic Cloud, the largest of the Milky Way's satellite galaxies. As you can see, it is brimming with nebulae. The one we're focusing on, the Tarantula, is the brightest and biggest one in that entire galaxy. And when I say bright, I mean bright. I selected this particular Hubble image because it still manages to show some of its intricate detail. Most other images I found simply show it as a bright, overexposed, blown-out spot of light. It is so intensely bright that if this nebula were as close to us as the Orion Nebula is in our own Milky Way, it would be bright enough to cast shadows at night. Let's zoom in to find out why. The Tarantula Nebula is currently undergoing a period of extreme, violent star formation. In fact, it is the most active star-forming region in our entire local group of galaxies. At its center is a massive region of stars, known as NGC 2070. And at the very core of that is a supercluster of stars, known as R136. This cluster alone, this one bright knot, is what produces most of the energy to make the entire nebula visible. It's a truly enormous cluster, with an estimated 450,000 solar masses contained within it. Now, if you have ever wondered what the most massive and brightest known star in the universe was, look no further. It is here. One of the stars in this cluster, known as R136A1, is the current record holder. Its statistics are almost nonsensical. It's a Wolf-Rayet star, 315 times the mass of our Sun, and it shines with a light of 8.7 million suns. It is also one of the hottest stars we've ever found, at 53,000 degrees Celsius. As always with these massive, brilliant stars, it will be incredibly short-lived. It will burn through its fuel in a cosmic instant, and will almost certainly collapse into a black hole at the end of its life. In the meantime, it's shedding its mass through ferocious solar winds. Since its birth, it's thought that this single star has already lost 50 solar masses back into space. The R136 cluster itself is thought to be only about 2 million years old, a mere infant. You may not think there are enough stars in this image to add up to 450,000 solar masses. But that's because these brilliant blue stars you see are only the very brightest, most massive O-type stars. They are just the tip of the iceberg. The drama of this region is staggering. Interestingly, there is a star that belongs to this cluster, but it isn't found anywhere near it. If we zoom out a bit, you'll find this star over here. It's called 30 Doradus 016. This young star, only 1 to 2 million years old, may have traveled about 375 light years from its suspected home in R136, and it's still traveling at 400,000 kilometers per hour. But how did it get all the way out here? The leading theory is a game of cosmic billiards. It was likely part of a binary star system, happily orbiting its partner when another, even more massive star blundered into the system. The chaotic three-body gravitational dance kicked out the now homeless star, flinging it into the void. And those other stars would have had to have been extremely massive, because 30 Doradus 016 is no minnow itself, and a suspected 90 solar masses. But this isn't the only story of violence here. There is another, older star cluster found in the Tarantula Nebula called Hodge 301. It's roughly 20 million years old. Its stars are, on average, 10 times as old as the infants in R136. And this is where we see the ghost of Christmas future. Within this older cluster, there are thought to have been at least 40 stars that have already gone supernova. In R136, there have been none. This is simply the effect of age. In Hodge 301, the shortest-lived, most massive stars have already lived their entire lives and exploded, seeding the region with heavy elements. More stars in this cluster are on the verge of exploding too. The original image we looked at is further away still, in an area called NGC 2060. This is another star cluster, though the stars here are much more loosely dispersed. In fact, they are no longer gravitationally bound to each other, and in a few million years, this stellar group will disperse completely. It's about 10 million years old, and there are some very interesting things here. First, the whole of NGC 2060 is a supernova remnant, about 165 light-years across. It's estimated this supernova occurred about 4,000 to 5,000 years ago. And consistent with this theory, a pulsar, a rapidly spinning neutron star, is found right in this area, around the same age as the remnant. It's not visible in this light, as it primarily emits X-rays, which means you need the Chandra X-ray telescope to see it. But it's there, right in the middle of this expanding bubble of debris. This pulsar rotates exceptionally fast, once every 16 milliseconds. But incredibly, it's not even the fastest rotating star in this region. That accolade belongs to this runaway blue supergiant, VFTS 102. This is, in fact, the fastest rotating star that we know of, spinning at a blistering 2 million kilometers per hour. It spins so fast that the star itself has been flattened into an oval shape, and a disk of material has been flung out from its equator due to the extreme centrifugal forces. It is suspected that this runaway star was once part of the same system as the pulsar. Before the supernova, they would have been two blue stars orbiting each other. One would have evolved faster, becoming a red supergiant. As it expanded, it would have started feeding its mass onto the other star, VFTS 102. This torrent of new material would have spun up VFTS 102 faster and faster, like a figure skater pulling in their arms. Then, when the red supergiant finally exploded in that supernova, creating the pulsar, the explosion would have ejected the other star, VFTS 102, at a tremendous speed, sending it hurtling through space. VFTS 102 fits this model perfectly, as it is both spinning rapidly and hurtling through space. Zooming out further again, we are getting to the edge of the Tarantula Nebula. At its longest points, this single nebula is an incredible 1,000 light-years across. I already mentioned this nebula is the most active star-forming H2 region in our local cluster, but it is also the biggest. If it were as close to us as the Orion Nebula, it would be twice as big in our sky as the Big Dipper. And because it is so bright, it would be visible during the day. At the far edge of this nebula is perhaps its most remarkable visual spectacle, and one that is very personal to modern astronomy. It's called SN 1987A, and it's a supernova remnant. It is a lot younger than any of the other supernova remnants we've looked at. In fact, it is less than 30 years old, astronomically speaking. The light from this supernova explosion hit Earth in 1987 and was visible to the naked eye. It was the first supernova observed since the 1600s, and the only supernova we have ever had a close look using modern-day telescopes. When it exploded, it was a blue supergiant. And I bet you are wondering, what are those bizarre, glowing rings? Well, They are the mass thrown off by the star thousands of years before the supernova. This was the star in its final phases, coughing and spluttering its innards out into space, much like a planetary nebula, but on a more massive scale. What happened next is pure cosmic theater. First, the initial brilliant flash from the explosion raced outward at the speed of light. As this light wave hit the rings, it lit them up like a flashbulb in a dark room. Then, years later, the slower-moving physical shock wave from the explosion, the actual debris finally arrived at the rings and slammed into them. This impact lit the rings up again, this time from the sheer kinetic energy of the collision, from the interactions between the ring's material and the debris. SN 1987A is now a true supernova remnant in the vein of Cassiopeia A, illuminated not by the echo of the explosion, but by the continual, violent processes between the supernova's debris and the material that surrounded it. This artist's illustration, which is based on real data, reveals the cold inner regions of the exploded star's remnants. This red patch here is where the Alma telescope detected tremendous amounts of dust. It is in this thick, obscuring dust that the leftover pulsar or black hole could be hiding, because so far, nothing has been detected where the star's core should be. To see through that dust, to find that hidden heart, we need more than just visible light. We need a new kind of eye. The James Webb Space Telescope has now been in space for over a year. The images it sends back of the universe continue to captivate us with their high-resolution detail and truly breathtaking beauty. However, and this may sound counterintuitive, it is often what the Webb telescope does not see, or rather, how it sees the invisible, that allows us to really shine a light on the universe's inner workings. This concept of seeing without seeing might sound strange, but it is a foundation on which much of modern observation of the universe is based. Through clever techniques, it allows us to understand the chemical composition of molecular clouds and nebulae. It lets us probe the makeup of atmospheres around distant exoplanets, and even find the existence of rings around tiny asteroids in our own solar system. The James Webb Space Telescope is uniquely placed to take advantage of these techniques, due to its unprecedented sensitivity and precision in the infrared spectrum. Let's begin with this image of NGC 346, a cluster of stars and its associated nebula, found in the Small Magellanic Cloud, 210,000 light-years away from us. NGC 346 is fascinating to scientists because the conditions here, specifically the low amount of metals, are very similar to the conditions that existed back when the universe was only 2 billion years old, during a highly energetic period known as the cosmic noon. This was a time when countless stars and galaxies were rapidly forming. By studying this relatively nearby, modern contemporary, scientists can get a much better idea of what that cosmic noon might have actually been like. But how do scientists know the metallic composition of these beautiful swirls of stellar matter? Just by looking at them. One primary method is by looking at emission lines. When gases get hot, say, because they have been warmed up by a nearby star, the atoms that make them up seek to dissipate that heat by emitting radiation. However, for reasons that are rooted in quantum mechanics, every single element can only emit radiation at its own specific unique set of wavelengths. This gives each element a distinct, undeniable chemical fingerprint. If you know the specific wavelengths of light given off by oxygen, you can always tell when superheated oxygen is the source of any light you come across. So by seeing this light, by reading these fingerprints, the James Webb Space Telescope can get a precise chemical inventory of this nebula. And Webb is particularly suited to this. Its infrared vision is much more able to pierce those obscuring dust clouds, like the one in SN 1987A, to see what lies at their heart. Webb's superior sensitivity here has allowed it to detect details that had never been seen before, including these small dark disks of dust that were forming around developing protostars. a sign that we may be witnessing the very beginnings of planets. However, these are by now fairly standard methods of observation, and what Webb is doing next is anything but standard. I started our last conversation by alluding to a beautiful paradox, this idea of seeing through not seeing. When it comes to the deep universe, we've learned that merely looking for the light emitted by objects is often not enough. It tells only half the story. For instance, not long ago, the Webb telescope imaged this. It is a vast, dark, cold scar across the stars. This is an ice cloud. More specifically, it is the Chameleon-1 dark molecular cloud, another, but very different, kind of stellar birthplace. As you can well imagine, an ice cloud, by its very definition, is not hot. It is not radiating brilliant, glowing light with those clear emission lines we discussed. It is a place of profound cold and stillness. So, how can scientists possibly learn its chemical composition? How do you inventory a fortress that sends out no signals of its own? Here, a different technique, a different kind of seeing, must be employed. And thanks to Webb's piercing vision, this new method can be brought to bear. I mentioned earlier that when atoms become excited, they release radiation at specific fingerprint-like wavelengths. Well, this process, it turns out, works perfectly in reverse. When cold atoms are struck by radiation, they can absorb that energy and become excited, a little warmer. This has a truly clever and profound implication. It means that if you can shine a continuous, smooth spectrum of light, like a blank canvas of all colors, through a cold gas cloud, you can watch to see which frequencies of light are blocked by that cloud, which colors are stolen from the canvas. Those missing frequencies, those dark lines in the spectrum, will tell you just as certainly what elements make up that cloud as if you had heated it to thousands of degrees and watched it glow. This, then, is the beautiful paradox of seeing by not seeing. You are not looking for a glow. You are looking for a shadow. Of course, this entire technique hinges on one critical component. You need a source of light behind the cloud you want to look at. Fortunately, the universe provides. This occurs naturally, thanks to all the distant, unaffiliated stars that send out their light from far behind the Chameleon-1 dark cloud. The light given off by a star is much more varied in its wavelength than the light from a specific gas. A star is a hot, dense object, and it provides that smooth, continuous light source, the perfect backlight needed to check for these absorption lines. There is, however, a problem. For objects as enormous and dense as a molecular cloud, they can be well, too dense. For all of history, these clouds have been like fortress walls, too thick and opaque for the faint starlight from behind to ever penetrate. This is where the sheer power of Webb comes into play. Thanks to the James Webb Space Telescope's unprecedented exquisite sensitivity, for the very first time scientists have been able to detect the faint filtered light from those distant stars as it passes through the thick, cold cloud of Chameleon-1. They were finally able to see its chemical composition. And what they found was, in a word, a surprise. It was a profound one. Not only does the Chameleon-1 dark cloud contain vast quantities of simple water ice as expected, but it also contains the fundamental building blocks of life. In this frozen, dark, silent void, Webb tasted the chemical signatures of ammonia, methane, and methanol. This means that the stars, and perhaps more importantly, the planets that will one day form within this icy cloud, will begin their journey pre-stocked. They will start off with these quite complex chemicals, a rich prebiotic soup, to get the ball rolling. And if this turns out to be common, if the universe's stellar nurseries are all, in fact, pre-seeded with the ingredients for life, it makes it that much more likely that worlds capable of bearing life are actually widespread. It is a deep, chemical hint that we are, perhaps, not alone in the cosmos. This science of spectroscopy, this art of studying the chemical makeup of objects from their light signatures, whether glowing or in shadow, is a versatile and powerful tool, and it extends to much, much more than just cosmic clouds or nebulae. Through this very same technique, we can also learn about the atmospheres of exoplanets. Recently, Webb was able to discover the precise chemical makeup of one such exoplanet. It's called WASP-39b, a colossal, Jupiter-sized, hot gas giant orbiting a star some 700 light-years away from us. How? By patiently waiting until that planet passed in front of its own star. For a few brief, precious hours, the light from that distant sun filtered through the planet's atmosphere on its way to Webb's mirror. The gases within that alien air absorbed the starlight at their own specific signature frequencies, leaving their distinct chemical fingerprints on the light that remained. In that stolen light, Webb detected sulfur dioxide. This was the first time this compound had ever been seen in an atmosphere outside of our solar system. And it is a fascinating find, as it is a molecule often created by active photochemical processes. Webb also provided a complete breakdown of all the other chemicals and elements present, including unmistakable signs of water vapor. We are, quite literally, tasting the air of other worlds. Spectroscopy, as impressive as it is, isn't the only way that Webb makes discoveries by not seeing. There is a second, perhaps simpler process, known as occultation, which astronomers have been making use of for the last century. But with Webb, it has become a tool of almost unbelievable precision. Rather than searching for the complex chemical breakdown of the starlight, watching for an occultation involves noting simply a star's brightness over time. By looking out for the sudden, brief, and complete dimming of a star, scientists can discern the presence and characteristics of dark, non-glowing objects that pass in front of them. It is the science of tiny, fleeting shadows. And the James Webb Space Telescope is very, very good at spotting such dimming moments. Let's bring it back to our own solar system. Out between the orbits of Saturn and Uranus, there lies a rather unusual little world called Chariklo. It is about 250 kilometers in diameter, and is the largest of a strange class of asteroids known as the Centaur's objects that tend to orbit in that chaotic space between Jupiter and Neptune. That, however, is not its claim to fame. Chariklo is impressive because in 2013, it was discovered to be one of only 5 objects in our solar system known to have rings. For a long time, scientists did not believe that an object as small as Chariklo could possibly support a stable ring system. Even now, they are unsure whether these rings are only here, because they are relatively new, perhaps the fresh debris from a collision in the last few million years, or whether some complex gravitational phenomenon, perhaps shepherd moons, too small to see, is keeping them in place. The James Webb Space Telescope tested its ability to observe these occultations by trying to spot these very rings as Chariklo passed in front of a distant star. This was not as easy as it sounds. It takes phenomenally precise predictions to know exactly where Chariklo would be in its orbit, to know which single star to watch at what exact second. Given the vast scales of space, even the smallest miscalculation, a tiniest fraction of an arcsecond, would result in no occultation being observed at all. That said, Webb was able, and it succeeded. It spotted Chariklo and its 2 rings. It watched the star, and the data it sent back was not a picture, but a graph of light. It showed the starlight, then a sudden tiny dip. Then, a moment later, another dip. Then, a long dip as the asteroid itself passed by. And then, on the other side, a dip and another dip, a perfect mirrored signature. The rings were, of course, far too small to be imaged by Webb directly. But from that sudden, rhythmic dimming in the star's brightness, Webb was able to clearly make out the rings, which are thought to orbit about 400 kilometers from Chariklo itself. The larger of the 2 rings is only 6.9 kilometers wide, and the smaller one, the one that Webb still detected, is a tiny 120 meters wide. It is not yet clear what these rings are made of, but Webb was able to detect the signature of crystalline water ice on the main body of Churyko. With further observations, more information about these mysterious impossible rings will surely come to light. And speaking of rings, there is one more image I truly want to show you. This is, for me, one of the most spectacular and baffling images Webb has yet produced. This is the strange, ethereal, reddish-purple set of rings around a star system known as Wolf-Rayet 140. These rings are like nothing I have ever seen in space before. When the astronomers who took the image first saw it, they genuinely thought that something might be wrong with their equipment. The rings seem more like the perfect concentric ripples in a pond, or the rings of a tree, than an actual, real interstellar object. And yet, these rings are real, and they actually do represent something like tree rings. They are a physical record of over 100 years of a truly incredible repeating phenomenon. At the heart of these rings lies a binary star system. Every 8 years, precisely, the two stars at the center of this system spiral in close to one another in their orbit. When they do, their two powerful, opposing stellar winds interact, colliding in such a way as to blow a fresh ring of carbon-rich dust outward into space. There are at least 17 rings visible here. This means this precise clockwork process has been ticking along every 8 years for the last 130 years or so. This phenomenon is enormous. The furthest ring is 70,000 times the distance from the Earth to the Sun. The detail Webb was able to capture here is just ... incredible. Previous glimpses of this system by other telescopes indicated that there might have been 1 or 2 rings, but the images were incredibly blurry, a faint smudge compared to the perfect resolution captured by Webb. These rings were more than just beautiful. They were useful. They provided astronomers with a unique opportunity to spatially document the chemical composition of each ring. And in doing so, scientists found what they believed to be polycyclic aromatic hydrocarbons, or PAHs. PAHs, essentially complex, soot-like organic molecules, had been known to exist in space for a long time. They are thought to be a crucial component in the formation of stars and planets. But their origin has long been a mystery. Now, thanks to this discovery by Webb, these Wolf-Rayet binary stars have stepped forward as one possible and very potent source for this crucial prebiotic compound. We have found a factory. And it was only possible because of spectroscopy and James Webb's astonishing ability to both see and not see light in incredible world-changing detail. There will, no doubt, be many, many more discoveries that Webb will make in the years to come. Such a powerful telescope can, of course, capture images at a far greater clarity than any of the space telescopes that came before it. But I thought it was important to emphasize that not all of Webb's discoveries are stunning, poster-worthy images of the night sky. Many of its biggest breakthroughs lie in the tiny, hidden details ... the things not seen. The light that fails to appear when it might be expected to, indicating the presence of hidden chemicals or unseen rings or the very air of a distant world. Because, as it turns out, it is not always about what you see. Sometimes, what you don't see is the most informative story of all. It is, perhaps, no wonder that this has been one of the most hotly requested topics for this channel. Even if you didn't actively request it yourself, you could not have missed the buzz around the James Webb Space Telescope. It is a machine that is, in itself, a work of art. It is more powerful than any other space telescope, including the venerable Hubble. It is so large, its 6.5-meter golden mirror had to be folded up like a piece of intricate origami to fit onto the rocket that would carry it into the dark. It is so precise and so sensitive to the very heat of its own electronics that it has to be kept at temperatures not much warmer than absolute zero, just to prevent its own internal heat radiation from getting in the way of its sensors. It is so expensive, it cost $10 billion to make. So complicated, it took decades to complete. and it was so delicate that over 300 potential single point of failure items stood between it and proper functionality. But now it is here, and it has an incredible three-part mission to study planetary systems, even our own, for a deeper understanding and perhaps even evidence of life. To understand the formation of planets, stars, and galaxies. And perhaps most profoundly, to peer out across the universe to objects so impossibly far away that the light they gave off has been traveling for almost as long as the universe itself is believed to have existed. In other words, the James Webb Space Telescope was built to spot the very first stars and the very first galaxies. It is a time machine built to see the dawn of our knowable universe, objects from the beginning of time. And the first images have been coming in. For those who are new to our journey here at Cosmic Whispers, we have spent some time watching this telescope as it has gone from a work in progress to a fully realized piece of hardware. It was first conceived in the 1990s and was originally, and perhaps optimistically, intended to cost only $1 billion and to launch in 2007. But, as we know, numerous setbacks and delays plagued the project, pushing it back again and again and again. It was only in December 2021 that it finally and flawlessly launched. It has been spending the intervening time slowly carefully unpacking itself, powering up its systems, and testing its hardware. It is a 6,500 kilogram monster. Its sunshield, which is what keeps it so cold, has dimensions of 14 by 21 meters, roughly the size of a tennis court. Its mirror, for capturing that faint, ancient light, is 6 times larger by area than Hubble's, which allows it to pick up more photons from further away to create these impossibly crisp images. It boasts numerous cameras and scientific instruments, all of which allow it to see across the infrared spectrum. This is the feature that is absolutely vital to its unique mission. Because of the expansion of the universe itself, all of the light from the furthest reaches of space has been stretched. Just like the sound of a siren is stretched to a lower pitch as it moves away from you, the light from the first galaxies has been red-shifted, stretched so far that no matter what color it was to begin with, it is now only visible as infrared light. So the only way to see these first light sources, these cosmic ghosts, is with a dedicated infrared telescope. On top of that, infrared light is, as we've learned, much better at punching through clouds of dust and other obscuring debris, giving Webb the incredible ability to see objects that are, and forever will be, completely beyond the sight of Hubble. I compare this telescope with Hubble a lot, as Webb was originally intended to be Hubble's successor. However, given their slightly different fields of view, Hubble seeing mostly in visible light, while Webb sees almost exclusively in infrared, it is more accurate to say that the two telescopes complement each other rather than compete. They work together. They are a powerful scientific duo, expanding our understanding of the universe in tandem. But that is enough about the machine. You are here to see what it sees. Let's begin in our own galaxy, and gradually we will expand our vision outwards towards the very edge of the knowable universe. You are in for some spectacular sights. The first stop on our journey is a place known as the Cosmic Cliffs. This region, otherwise known as NGC 3324, is part of the Carina Nebula, about 7,600 light-years away from us. These peaks you are looking at, these cosmic mountains, are massive structures, around 7 light-years high. And what you see here is only a small portion, an edge, of a nebula as a whole. The actual nebula is much larger. It contains a vast, hollowed-out center where the fierce stellar winds given off by newborn stars have blasted all the nearby dust and gas away from them. What we are looking at here is the rim of that hollowed-out bubble. Scientists are intensely interested in this region of space for one simple reason. It helps answer questions about the formation of stars. Thanks to those stellar winds, the dust and matter in this wall are being compressed, conglomerating together, forming the next birthing place for a new generation of stars. However, for all our stargazing, there are still many, many mysteries surrounding this process. How exactly do they form? What do the different stages look like? It has always been difficult to tell. And part of the difficulty is the dust itself. The very dust that is vital to the process is also a massive impediment to seeing that process happen. It wraps around the forming stars like a protective natal cocoon, stopping scientists from seeing clearly what is going on at the very moments we would like to see the most. Webb fixes that. Not only does this image provide more detail than Hubble's, but thanks to Webb's onboard MIRI, or mid-infrared instrument, we can peel back the layers of dust and see what lies within. Look at this. See how much clearer the image becomes in the mid-infrared. The dust, which was opaque, becomes as transparent as glass. We can see through the mountain. This will provide scientists with data on the formation of stars for a long, long time to come. So much for the birth of stars. At our next stop, the James Webb Space Telescope uncovers more about the end of their lifespan. And for this, let's look a little closer to home, to NGC 3132, otherwise known as the Southern Ring Nebula. The image on the left was taken by Webb's near-infrared camera, while the one on the right was taken by its mid-infrared instrument, a MIRI. This is a planetary nebula, although, as we've learned, that term is a bit of a misnomer. While regular nebulas are the birthplace of stars, a planetary nebula is not a place where planets form. Instead, it was just an unhelpful naming convention, used by early astronomers who noted the round, planet-like shapes of these nebulas in their small telescopes. The name, unfortunately, stuck. Planetary nebulas, like this one, are formed when vast shells of dust and gas are blasted out from dying stars towards the end of their lifetimes. Knowing the chemical composition of this dust is useful, as understanding what material is ejected back into the universe helps us understand what later waves of stars might be made of. So once again, Webb's ability to peel back the layers of dust to see what lies within is invaluable. Compare this to Hubble's image. The increased detail is astonishing. But it's not just prettier. From this, scientists have learned that the second star, deep within the system, has not yet exploded. We are seeing in real time how the complex gravitational interactions of these two stars are stirring the nebula, mixing the dust and gas together into these fascinating, intricate patterns. Now, let's look a little further out beyond our galaxy. If we want to see star creation on a massive scale, it makes sense to find a location like this. 161,000 light-years away from us, in a large Magellanic Cloud, lies the Tarantula Nebula, so named because it evokes the idea of a giant spider lurking within its silken web. This area is of particular note to scientists. Aside from its obvious otherworldly beauty, it is of interest because of its chemical similarity to a period in the universe, as history known as the Cosmic Noon. At that point, which to our best understanding took place about 1 billion or 2 years after the universe began, star creation was at its most prolific, its most frenzied. It is thought that the conditions in those early star-bursting galaxies would have looked something like this. And with its infrared eyes, Webb has been able to pierce the dust of this region and spot stars that are only just coming into being. A fascinating and previously invisible period of time to study. Let's look further out again. As our gaze extends, we lose track of individual stars, and we start to see things on a truly galactic scale. And even here, there are beautiful, slow-motion dances being played out. This is Stephan's quintet, a formation of 5 galaxies, although one is not really next to the others. It's a photobomber that just looks that way from our perspective. Famous for being featured in the film It's a Wonderful Life, this grouping is a true cosmic laboratory, It is thought that 4 of these galaxies will, one day, collide and merge. Indeed, 2 of them are already doing so. Webb allows us to see, with perfect clarity, the brilliantly hot dust and gas being kicked off the shockwaves as these 2 central galaxies circle each other. The gravitational forces here are mind-bogglingly intense. The energy, profound. It is a dance that is truly only appreciable at scales like this one. This image, by the way, was not taken at a single time. It is actually a composite mosaic of almost 1,000 separate images that Webb took, which scientists then stitched together, giving it this incredible resolution for picking out those tiny, wonderful details. Let's look further out again. Further until even the James Webb Space Telescope is straining to see. This image is known as Webb's first deep field. It is taken from an area of the sky so impossibly small that a single grain of sand, held out at arm's length, would completely block it from your view. At this scale, individual stars are almost completely absent. Most of what you can see here, the thousands of points of light, they are not stars. They are galaxies. Here, you can clearly see the fisheye lens effect, the distortion created by gravitational warping. As the relatively nearer objects and clusters of galaxies bend and magnify the light from the objects behind them, we are, truly, starting to see the edges of the universe. In this image, hidden among the swirls and dots, is one of the oldest galaxies we have ever sighted. It is so far away the light from it, when it was born at the very beginning of the universe, has only just reached us. Where is it? We are going to need to zoom in. Do you see it? That tiny reddish smudge. It is, admittedly, quite small. By evaluating the markers within the light given off by this tiny red galaxy, scientists are able to identify how far it has redshifted, and thus, how long the light from it has been traveling. This tiny dot was found to be 13.1 billion light-years away. As far as we know, given that the universe is thought to be about 13.7 billion years old, this is one of the earliest galaxies that we will ever be able to see. Now you might be disappointed by how small and faint it is. However, there is some room for hope. Compare this image with one taken by the Hubble Space Telescope of the exact same region. Obviously, Webb's image is crisper, clearer, giving more detail and showing thousands more objects. But there is one vital, mind-blowing distinction between these 2 images. Hubble took its deep field image by staring at this patch of sky for 10 days, slowly, patiently, gathering every single photon it could. The James Webb Space Telescope took its own image in only half a day. What this implies is that if Webb was able to take such a detailed, profound image, revealing one of the oldest objects in the universe, in just 1/20th of the time imagine how detailed an image it could take if it was given a comparable amount of time. Imagine what we will see when Webb stares at this patch of sky for 10 days. In other words, this tiny little dot is likely not the best that Webb can do. This is just the beginning. I hope these images have given you a sense of the scientific breakthroughs that are now possible, but also just how achingly beautiful the sights of our universe are. We are going to have to be a little patient to see what other discoveries Webb might have in store for us. It has only just finished its calibrations and is now beginning its true scientific mission. There are, as you can imagine, queues of scientists, all with their own profound questions waiting for their turn to use it. Each second of its time is hotly contested. It will be investigating exoplanets, searching for signs of hospitable atmospheres for life. It will be unveiling the dusty hearts of nebulae to find the true origin of stars. And it will help us understand the difference between an old, mature galaxy like our own and the young, infant galaxies that formed just after the Big Bang. With a tool as powerful as this, a new set of eyes for all humanity, who knows what else we are about to discover. If these ideas of our shared cosmos stir something in you, I hope you'll join us again, here at Cosmic Whispers.